Hello, good afternoon. I'm Rob, and I'm going to be talking about fiber diameter predictions through phase function analysis. So my project is to do with respirable fiber detection from light scattering patterns. And this is just sort of part of the process because I'm interested in finding an aspect ratio. And to start, I thought the easiest part would be to find diameter. We've got instruments at University of Hertfordshire that collect forward scattered light from aerosolized particles, and we've got a basic idea on how to distinguish between different aerosol types. So we know these are spherical particles or droplets. Just because of the concentric rings around them and stuff. And then you get more amorphous sort of particles like dust. And it's quite easy to see the difference between like fibers and these other particles. But what we don't know is a way of getting a more morphological information from these. And I'm hoping to do that with some techniques that I'll go through. To fit in with WHO regulations of like mineral fibers such as asbestos, because the detection of these things is necessary in prevention of deposition within the lungs, because we all know that asbestos is really bad to breathe it in. And there's also been links between other fibers and their aspect ratio and the toxicity. So what I've started doing is just looking into the phase function, and the phase function is it's like a slice of the scattered light. Let me start again. So we shine a laser at an aerosol particle, and light is scattered in all directions around it. And I've been looking at this like bright band in the middle, and I just take a slice of that, and sorry about these are so small, but it doesn't really matter. And you can see the band laid out in 180 degrees of scattering. So to start, what I did was, for a better idea on how this all worked and to sort of validate some models that I was going to use, I made a experimental setup to collect phase function data from fibers. So the fibers were mounted in a fixed position on a rotational stage. A laser shone at it at normal incidence, and the stage was rotated, and the data was collected with the PMT, and then converted into irradiance, and then I used SEM to compare, or to figure out the actual diameters of the fibers. I used two different fibers, one carbon and one glass. Unfortunately, they're a lot bigger in diameter than what was required for the WHO limits, but a lot easier to handle. I can barely see 5 micron fibers, let alone pick them up and handle them without them breaking and swearing at them quite a lot. So going down to 3 microns would be a bit of a pain. And here's how it looks. Sorry about the mess. But so the fibers will be mounted in this little 3D printed thing here, and the laser focused to the center of the rotational stage, and this other laser is just for alignment. This is rotated, and readings are taken at the PMT in each increment. So what I got from the SEM was the carbon being about 7.3, the glass being about 5 microns. And both the phase functions showed expected results. The carbon matched really well with diffraction, as you'd expect, because it's got a really high imaginary refractive index. And the minimum location points matched up fairly well on forward scattering, but they deviated quite a lot as it went further back. And a lot of the readings from the PMT were distorted by noise after certain angles, and pretty useless, really. So, and here they are. So you've got pretty good matching with forward scattering for the carbon, but yeah, they deviate quite a bit after a while. And the glass looks awful because I think I may have calibrated some stuff wrong, but it it looks similar. And when you look at the minimum locations, which is these little red stars, they do match up fairly well. And this I've used three different models. One diffraction because it's nice and simple, one me because it's quite numerically correct, and one discrete dipole approximation because I wanted to use something that could eventually include a finite length rather than me, where I'm just you're limited to infinitely long cylinders. So this sort of influenced the next step, which was to use these minimum locations, or the first minimum location, for predictions, and especially if I'm limited to forward scattering, it's going to be easier just using the one because they get quite small, and then as they get smaller, the phase function stretches out. But with the results earlier, like all this horrible stuff at the back, that was the result of the increased gain of the PMT to compensate for the high dynamic range that is found with scattered light. The further back you try and find a minimum value, it's probably going to be completely disappeared in all this. So I had to come up with another idea, and that was using a section of the phase function. I fit a linear fit to it, line, and then take the gradient of that. And what am I talking about? I've lost where I am. I think I'm doing good. So basically what I did was I made a lookup table. So I had an assumed refractive index of 1.5 plus 0.5, and did the whole range that I needed to go through of different diameters using me theory. I did check whether there was any length dependence using the discrete dipole approximation, but it seems to be different. Yeah, so even I'm confused about this sometimes. So this is the phase function, and what I'll be doing is collecting the gradient of this line between these two limits for the smaller particles, because they have a more stretched out phase function. And this is the 26-degree line, which is the limit of a lot of the instruments we have. And if they're within, if the minimum point is within this limit, we can use that for prediction. I don't know why that says 16 there, never mind. So yeah, I created a lookup table and then made 10,000 randomly sort of generated phase functions between these diameters. 0.02. I didn't think going any smaller than that would be very useful. And the high limit of the WHO regulations is 3 microns. And I also randomized the refractive index between 1 and 2 plus 1. And interpolated the data through the lookup table that I made, and I got this. And so these are the gradient ones, the smaller diameters, and these are the larger diameter ones using the minimum points. And they all seem to fit pretty well. They're all round about 0.9 as an R² value and less than 0.05 for a P value, which I think is good. And I did get some negative results, and this is probably due to the fact that 2 minutes, cool, no worries. The fact that interpolation is quite unreliable, but I want to use it because it's a nice way of a direct measurement, and that's pretty much it. But yeah, I'll be hopefully using this in the future to use with our machines that we have, and then length measurements and stuff as well. And I'm sorry I ran over time there, but that's pretty much it. Thank you.